this idea of the dragon hatchling, the missing link between the transformer and models of the brain. And so, a couple weeks ago, we talked about this sort of link between like these machine learning models and models of the brain and some of these things. And this got posted. So the Dragon Hatchling is kind of a provocative title. But what do they mean by that? So let's see. This is from, these people are from Pathway, which I guess is a startup in Palo Alto. I'm not familiar with it, but that's kind of where they're coming from, is from a sort of maybe a tech startup standpoint. So the relationship between computing systems and the brain has served as motivation for pioneering theoreticians such as John von Neumann and Alan Turing. Uniform, scale-free biological networks, such as the brain, have powerful properties, including generalizing over time, which is the main barrier for machine learning on the path to universal reasoning models. I'm wondering why they're using uniform and scale-free as descriptors of the brain. Maybe we get to that later, but we'll see. We introduced the Dragon Hatchling, or BDH, a new large language model architecture based on a scale-free, biologically inspired network of n locally interacting neuron particles. So this is a network model. It's scale-free. We have these particle systems that are locally interacting. BDH couples strong theoretical foundations and inherent interpretability without sacrificing transformer-like performance. BDH is a practical, performance, state-of-the-art, attention-based, states-based sequence learning architecture. So this is states-based sequence learning is the key here. In addition to being a graph model, BDH admits a GPU-friendly formulation. It exhibits transformer-like scaling laws. So we find empirically that BDH rivals GPT-2 architecture transformer performance on language and translation tasks at the same number of parameters, 10 million to 1 billion for the same training data. So 10 to the 6th or 10 to the 7th to 10 to the 9th parameters. BDH provides theoretical foundations for understanding model behavior in the limit of large size and reasoning time. Our results, formalized as a chain of reductions of expressiveness in the framework of computational complexity theory and distributed computing, and combined with findings on the BDH model, show a macro to micro correspondence of function between the general attention mechanisms in state-of-the-art language models and attention mechanisms observed in the brain. So they're actually able to get this sort of correspondence of function between the two. I don't exactly know how they determine that, but these attention mechanisms formally converge as closed-formed local graph dynamics at neurons and synapses, the equations of reasoning. So they basically build, and this is something that this is kind of an emerging theme in the literature, where you're using these closed and open graphs. So like, you'll have a graph where it's connected, and that's a closed graph. And then an open graph is where you need to insert a node to get a certain relationship. So, you can use closed form graphs to describe things. You can also use open form graphs to describe things. And, it's basically, if you have the graph itself is the representation that you have or the data that you have. If you can describe what you need with the data that you have, that's great. It's a closed form graph. If you need additional data, or if if the graph needs to add a node to get that kind of description, then that's an open form graph. So I kind of go over that in this spatial intelligence talk towards the end, and looking at the work of Saffron et al. On they're doing some things with open form graphs, and kind of go through that a little bit. So that's kind of an interesting theme to follow up on. So it's interesting, they call neurons and synapses the equations of reasoning, or at least these graph representations of neurons and synapses, the equations of reasoning. You put it in quotes because that's always good. BDH can be represented as a brain model. It contains N neurons organized as excitatory circuits and an inhibitory circuit with integrate and fire thresholding of input signals at neurons. The working memory of BDH during inference entirely relies on synaptic plasticity with Hebbian learning, using spiking neurons at potentiation scales of minutes for the brain, up to hundreds of tokens. We confirm empirically that specific individual synapses strengthen connection whenever BDH hears or reasons about a specific concept while processing language inputs. The neuron interaction network of BDH is a graph of high modularity with heavy-tailed degree distribution. The BDH model is biologically plausible, explaining one possible mechanism which human neurons could be used to achieve speech. Then BDH is designed for interpretability. Activation vectors of BDH are sparse and positive. We demonstrate monosemantically in BDH on language tasks, including representation of concept abstractions, which happens even for small models below the 100 million parameter scale. Interpretability of state, which goes beyond interpretability of neurons and model parameters, is an inherent feature of this architecture. So we believe BDH opens the door to a new theory of thermodynamic limit behavior for language and reasoning models, with the ultimate goal of probably approximate correct or pack-like bounds for generalization of reasoning over time. So they have a technical blog entry and a GitHub repository for this. And this is their company pathway. So the abstract kind of reads a little bit like marketing materials, but also has some very nice things in it. These promising things. So this is they have a table of contents, the introduction, and then BDH, a language model architecture given by local distributed graph dynamics. This is exciting to me because they're actually using some elements of network theory here to describe some of the things that are going on in this. So, we're talking about different graph formalisms, first of all. And, we're using these graph-based language models. We're also defining this approach BDH as a local edge reweighting process. These are what they call the equations of reasoning. Interpretation of attention as a microinductive bias of reasoning. Interpretation of BDH as an oscillator network toy model, and then expressing BDH using brain models. And then, so that's kind of maybe the heart of the paper that I'm interested in personally. There's also BDH GPU, a tensor-friendly version of the BDH architecture, so they about implementing it on a GPU. Actually, they have the state space system definition here, the local interacting particle system, and then preserving parameter and state size. Then they have some section on scaling laws, the emergence of modularity and scale-free structure, linear attention, sparse positive attention, and monosemanticity. Then playing with the hatchling, where they're doing model merging and training without backpropagation through time. So yeah, then let me go down and see if they have some figures. So yeah, this just shows like tensor-based models where you have centralized computing versus local graph models or distributed computing on graphs. So this shows the attention mechanism, local dynamics, and this feed-forward network. So the tensor-based models, which is indicative of centralized computing, you have the transformer, and then this BDH GPU. So they compare those two for the tensor-based model. So this BDH GPU is actually a different type of model than the BDH that they talk about. So in a transformer, you have a general attention mechanism. the attention mechanism for the transformer is a KV cache. For the BDH GPU, it's a state matrix and neuron dimensions. Then the local dynamics for the transformer is a linear algebra. For BDH GPU, it's a local mean field dynamics. And then the feed-forward network for the transformer are these MLPs. And then you have these weight matrices. And then BDH GPU, you have this emergent network defined by decoder, encoder matrices, and then these neuron dimensions. So they kind of use, I don't know if they're using reservoir networks or what they're using for this, but we'll maybe get to that later. The local graph models, on the other hand, and then, okay, so that's the tensor-based models. There's this general attention mechanism that they're trying to approximate here. And then local graph models, we have the attention mechanism, the local dynamics, and the feed-forward network. So local graph models are distributing computing on graphs. So we talked a little bit about how they're using sort of complex networks instead of neural networks for this, or at least the way they're describing it is more in the complex networks domain. So BDH, for the attention mechanism, is synaptic state plasticity, and there's a parameter for that. And then synaptic state plasticity is also the case for brain models. The local dynamics consist of local graph dynamics plus edge reweighting for the BDH. And then brain models, we have spiking graph dynamics plus Hebbian learning. And then the feed-forward network for the BDH are neuron interaction graphs. And so there are these graphs here defined by X, Y, and S. And then for the brain models, the feed-forward network consists of neuron interaction graphs, which are unspecified. So these are general overview of these architectures. The inference dynamics of BDH and BDH GPU act as a natural bridge between transformers and models of the brain. The two main inference mechanisms of a reasoning architecture, attention and the feed-forward network, are defined at a macro level through tensor operations for the transformer, and at the micro level, neuron interactions through local graph dynamics for brain models. The new BDH GPU architecture is naturally defined both at the level of vectors and of particle dynamics of neurons and synapses, acting as the bridge between the two approaches. Okay, so this is the physical system representation of BDH as a physical graph toy model. So this just shows these different graph parameters, GX, GY, and GS. You see them here. I guess there are connections between these different states. You have X and Y as the activation vectors, and then you have synaptic state of model. So the graph parameters of the model. So you have, first of all, you have state equations, and then you have the oscillator network toy model. The state equation for our graph parameters of the model. In the oscillator toy network model, the correspondents are wires, prods, and elastic connections. So that's what they have here. They have these elastic connections, wires, and prods. And then the synaptic state of model corresponds to the displacement of elastic connections in the oscillator network toy model. So this is the toy model, and I think what they're trying to do here is diagram out these different components. And, you know, it's kind of like they're taking things from their state equations and kind of translating it to this sort of graphical model. So you have these elastic connections, then you have the displacement of elastic connections, then activation vectors, the state equations, the correspondence of that, and the toy network, oscillator network toy model are pulses at nodes and state correction. So that's what they're kind of describing here. Okay. So they have a lot of equations in here I'm not going to go through. And this is neuron-neuron communication using graphs. So this is the correspondence between graph H, which is here, with M edges, which is on the left, and neuron-neuron interaction graph G, which corresponds to H squared. So basically, this just shows how you can express linear signal propagation on a broad class of graphs using 2 steps of linear dynamics on a sparse circuit. So I'm interested in this toy model, and the toy model, of course, is usually, we'll use a toy model in physics to demonstrate a principle that's kind of hard to understand, and you build this small model that isn't necessarily useful for large amounts of data, but nevertheless it communicates this idea. So I want to go over the definition of the toy model because I think it's interesting. So we will consider the toy model of an n-particle system shown in the figure that I showed in figure 2 is an illustration of the general form of dynamics of the state space equation of BDH. All right, so the first thing is we draw n particles in a circle. We see that here we have the 5 particles. And then the particles are connected with each other by the state elements, represented as these elastic connectors, these wiggly lines. The topology of the pairwise connections is given by the graph GS. So that's the black lines between the states, and may in general be dense. The signal displays dynamics of state P through or phi through tension on connectors, which evolves at a slower time scale and a more pulse-like activation dynamics XY on nodes, appearing and vanishing regularly at a rapid time scale. So that's kind of what they're doing here. So they basically have these elastic connections between the nodes. Then they have this tension that introduces these pulses, and that's kind of how they're imagining their network. The slower state dynamics represent in the first order oscillation or relaxation of the system of elastic connectors. Once an elastic connector between particles I and J has had its endpoints displaced through states X and Y, respectively, a tension appears on this connector, which causes its displacement. And so then, between the particles. So there's this displacement between the particles when you get this sort of tension in the system. So it's like kind of combining a physical system with the actions of like a spiking neural network or something where there's some sort of synapse or connection between the two neurons. So it's interesting. And, we've talked in DevoWorm, we talk a lot about tensegrity models. And this is almost kind of giving me the same kind of idea about how those models work. We have a number of nodes in the model, which are mechanical points of articulation. And then we have these strings that can induce tension or, some other physical constraint. And they behave in a way that, introduces superstability to the system. So the physical forces balance out. That seems kind of like what they're trying to do here in a way. They're trying to build this physical system that represents kind of the, what you might see in a neural system. And I know there are a lot of like analogies being made here, but I think they're onto something, because there are a lot of these sort of thermodynamic approaches that people are starting to pick up now in the field. And so, but it's interesting how they're trying to kind of find the right mix of things. So the faster dynamic, back to this definition of a toy model. The faster dynamics represent the node dynamics of particles. Over time, pulse displacements xi happen at nodes as a result of either previous behavior of the system or perturbation by an external forcing field. Okay, so this field would be a language input, or it could be some other type of thing that you're trying to analyze, like data for classification or something like that. A node I with displacement xi may, due to the exaggerated action of tension of elastic connectors adjacent to it, activate a system of prods gy adjacent to it, perturbing nodes it hits in this way. If another node j is prodded sufficiently hard, it may cause it to activate a perturbation Yj. Perturbation Yj of a node J will, in the next step, propagate action to those other nodes I', which are connected to J by a system of wires. Yeah, this is definitely sounding like tensegrity. I'll have to pull this up, or at least think about this in that context. Because in tensegrity models, you have single nodes that interact with other nodes, but you have both these direct connections and these indirect connections, or at least indirect effects that you see. So node I is connected to node J, and then node K is also connected to node I and node J. And when you perturb I, or when you perturb a connection with I, it perturbs the connection with J and K, and then that propagates back to I. So you get this feedback as well. So you get this mass set of effects from a single propagation, and that's largely due to the connection. They're all being connected in a network. If the aggregated pull of wires on a node I' is sufficiently strong, this modifies its pulse displacement xi'. The pulse activation Yj' of some node J' directly following the pulse activation of xi' of node xi' results in an increase in the tension of the connector Ij, adding to the value of the tension. All pulse activations Y subside and the pulse propagate, consequently altering the slow state. So this is kind of describing how these relations happen in the network using a very simple set of interactions that we can unpack. So I like that, that aspect of it. I'm not quite sure about if I can answer my question about the type of methodology they use for network. I don't think they use any sort of reservoir network here, but it would be interesting to use that to grow the graph. They do use edgery weighting, so they use a closed graph with edgery weighting. I think that's what they're doing here. They also have this sort of anchoring definition. So for anchoring in the literature of dynamical systems, we note that already systems following an interaction kernel with a strongly constrained K in the form K inclusive of Ij exhibit powerful nonlinearities, which is what we talked about before in the toy model example. With such a restriction on K, equation 3, which is up here, this equation, which looks like a replicator equation, describes the class of evolutionary systems following the equations of replicator dynamics. And this was from Hofbauer and Sigmund, also equivalently known as non-normalized form of the fundamental Locke-Volterra predator-prey dynamics. So this is a replicator equation here, which describes sort of, where things replicate based on their fitness. And if one class of replicator is dependent on the other class of replicator, they sort of regulate their reproduction and their ability to replicate. Replicator dynamics can naturally be represented as graph systems whose parameters are defined on edges on the graph, but whose state is updated on nodes on the graph. So the parameters are edges, the states are nodes. By contrast, when defining dynamics for reasoning in the current work, we will also need to capture a more powerful class of graph-based systems where, crucially, state is larger than the number of neuron nodes appearing on neuron edges or synapses.